Reinforcement learning from human feedback, or RLHF, has historically been a nightmare to scale. Standard PPO is notoriously unstable and computationally heavy. But what if we could bypass reward modeling entirely? Welcome to Direct Preference Optimization, or DPO. Today, we are dissecting the math, the architecture, and the code-level intuition behind it. Traditional RLHF using proximal policy optimization requires 4 distinct models in memory: the actor, the critic, a reference model, and a reward model. That is a massive distributed systems problem. DPO simplifies this radically. By reparameterizing the reward formulation, DPO eliminates the critic and the reward model. You only need the model you are training the policy and a frozen reference model. This turns alignment into a straightforward, supervised learning problem. To understand DPO, we start with RLHF models human preferences using the Bradley-Terry model. It assumes the probability that a user prefers response A over response B depends on the difference in their latent rewards. If the reward for A is significantly higher than B, the sigmoid function pushes the preference probability toward 1. Standard RLHF trains a separate neural network to estimate this reward scalar. But DPO asks a brilliant question: can we extract this reward implicitly directly from the language model? Here is the core mathematical trick of DPO. An optimal policy in RLHF maximizes expected reward while penalizing the KL divergence from a reference model. Through algebraic manipulation, the authors showed you can solve for the optimal reward function purely in terms of the optimal policy's probabilities and the reference model's probabilities. Specifically, the implicit reward is proportional to the log ratio of the policy probability over the reference probability, multiplied by a penalty factor beta. The reward model is effectively embedded inside the language model itself. Substituting this implicit reward back into the Bradley-Terry model gives us the DPO loss function. We minimize the negative log likelihood of the preferred response over the rejected response. Look at the equation. We calculate the log ratio of the preferred completion, subtract the log ratio of the rejected completion, scale it by beta, and pass it through a log sigmoid. This objective naturally pushes the model to increase the likelihood of the winning response and decrease the likelihood of the loser, smoothly bounded by the reference model. Let's examine the gradient of this loss. When you differentiate the DPO objective with respect to the policy parameters, you uncover a beautiful weighting mechanism. The gradient is the difference between the gradients of the log probabilities of the winning and losing tokens, scaled by an implicit reward error term. If the model is currently assigning a higher implicit reward to the losing response, this weight approaches 1, forcing a strong update. If the model already confidently prefers the winner, the gradient gracefully decays to 0. At the code level, during the backward pass, PyTorch routes gradients through your transformer. Because we have paired data winner and loser sequences, we compute the forward pass for both through the policy and reference models. Gradients originate at the language model head, where the cross-entropy over tokens is manipulated by our DPO loss. Positive gradients flow into the parameters associated with the winning tokens, and negative gradients suppress the representations of the losing tokens, propagating all the way down through the self-attention blocks. The most critical hyperparameter in DPO is beta. Beta controls the strength of the KL divergence penalty. A higher beta means the policy model is heavily constrained to stay close to the reference model, resulting in smaller, safer updates. A lower beta gives the model more freedom to maximize the margin between winner and loser, but risks catastrophic forgetting and generating out-of-distribution text. In practice, betas is usually tuned between 0.1 and 0.5 depending on dataset variance. DPO isn't the only preference optimization method. Identity Preference Optimization, or IPO, alters the loss to add a regularizer that prevents the model from over-optimizing on a finite dataset, avoiding the unbounded reward hacking DPO can sometimes suffer from. Then there's Kahneman-Tversky optimization (KTO). Unlike DPO, KTO doesn't require paired preference data. It just needs binary signals, thumbs up or thumbs down. This makes data collection significantly cheaper while achieving parity with paired DPO performance. Let's talk data pipeline. Quality is everything. A standard DPO dataset contains a prompt, a chosen response, and a rejected response. Often, teams generate this synthetically. You sample multiple responses from a strong model and use an LLM as a judge to score them. To prevent the model from learning shortcuts, the chosen and rejected responses should be closely matched in length and style. Always filter out pairs where the reward margin is near zero, as they provide no useful gradient signal. VRAM is a massive bottleneck in DPO. Standard supervised fine-tuning requires holding the model weights, optimizer states, and gradients. DPO doubles the weight requirement because you must keep the reference model in memory to compute the base log probabilities. For a 7 billion parameter model in BF16, the model alone takes 14 gigabytes. The reference takes another 14. ADAM-W optimizer states take 28. Add activation memory for 2 sequences, and you easily exceed 80 gigabytes without optimization strategies. To mitigate VRAM and compute costs, we rely on mixed precision. But DPO introduces a unique numeric instability, subtracting log probabilities. If both probabilities are very small, their difference can cause catastrophic cancellation in standard float 16. Always use float 16 for the forward pass, as its wider exponent prevents underflow. However, keep the master waster weights and the optimizer states in pure floaty 32. PyTorch's automatic mix precision handles this seamlessly, but verify your log sigmoid outputs aren't collapsing to NaN. Because DPO processes 2 sequences chosen and rejected simultaneously, sequence length drastically impacts memory. Activation memory scales quadratically with sequence length in standard attention. You absolutely must use flash attention too. Flash attention fuses the softmax and matrix multiplications, avoiding materializing the massive attention matrix in high bandwidth memory. It keeps VRAM usage linear with sequence length, which is mandatory when doing DPO on long conversations or complex reasoning traces. If you don't have large multi-GPU clusters, LoRa and CLoRa are your best friends for DPO. In a LoRa DPO setup, you don't need a separate reference model physically duplicated in memory. Instead, you load the base model frozen in 4-bit quantization. This frozen base acts as your reference model. The policy model is just the base model plus the trainable low-rank adapters. To get the reference logits, you simply disable the adapters during the forward pass. This slashes VRAM requirements by over 50%. Learning rates for DPO must be tiny. If your supervised fine-tuning learning rate was 2E5, your DPO learning rate should be around E7 to V6. Why? Because the policy model is already fine-tuned. Large gradients will rapidly push the policy away from the reference model, causing the KL penalty to explode and the loss to oscillate wildly. Use a cosine decay schedule with a brief warm-up to stabilize the optimizer momentum before making significant adjustments. When monitoring a DPO run, the loss curve alone is misleading. You must track 3 specific metrics: policy win rate, chosen reward, and rejected reward. The implicit reward of the chosen sequence should steadily increase, while the rejected sequence reward decreases. The margin between them should logically widen. However, if the policy win rate hits 100% too early, your model has over-optimized and simply memorized the dataset. A healthy DPO run typically stabilizes at a win rate around 75 to 85%. Debugging DPO failures usually points to 3 culprits. First, mode collapse. The model outputs repetitive gibberish. This means beta is too low or your learning rate is too high. Second, zero margin improvement. The model isn't learning preferences. This usually means your paired data is too ambiguous or length discrepancy is acting as a confounder. If the rejected response is always shorter, DPO just learns a heuristic to generate longer text. Always strictly control for length during your data curation phase. Direct preference optimization revolutionized LLM alignment by proving that complex reinforcement learning algorithms are not strictly necessary for injecting human preferences. By mathematically mapping the Bradley-Terry reward model directly into the cross-entropy loss of a language model, DPO gave the open-source community a stable, compute-efficient way to train state-of-the-art models. Whether you use standard DPO, IPO, or KTO, mastering this implicit optimization is a fundamental skill for any modern machine learning engineer. Happy training!